Hey everyone, so as we continue on with our discussion of forces and Newton's laws, we talked about at the beginning that forces are the answer to the question why, right? Why do these types of motion occur? Why do things speed up? Why do things slow down? Why do things not accelerate at all? Why do things not move? So no discussion about forces would be complete unless we discussed this force, friction. Friction is something that affects all the motion that we experience and that we observe and that we measure here on Earth, where the vast majority of our experience exists. So it's worth us talking about because almost all the situations we encounter, we have to deal with friction. We have to account for friction, unless you're like an astronaut that goes in space. So friction occurs at the microscopic level, and even if we want to talk about at the atomic and the subatomic level. So they take this, in the figure to the right over here, they take this little cross section, they blow it up. This box, while it looks smooth on its surface, is not. It's made of atoms, and if you recall from chemistry class, right, the boundary of an atom is not a fixed set, it's not a fixed system, right? Electrons can move around the nucleus in kind of a random fashion, and where the quote-unquote edge of an atom is kind of undefined. So where the edge of this box is, even though it may be smooth, it may appear to be smooth to us, it really has inconsistencies in its surface. And those inconsistencies also exist with the surface of the floor. So because we're dealing with protons and electrons at the surface or at the edge of two objects, we're dealing with charged particles. Those charged particles can repel or attract each other depending on likes and opposites and all kinds of stuff like that we'll get into later in the course. As they move across each other, certain times atoms might line up in a way that they want to attract each other. Certain times they might line up in a way where they want to repel each other. And that causes this resistance opposing the motion of the surface and the resistance of the motion as two surfaces come across one another. So, frictional forces resist motion. We're going to expand on that definition here in a second, but for now, we'll start with that. Let's talk about the type of friction that most of you would probably give me an example of if I asked you what is friction. So we have a box that is being pulled along the floor, let's say at a constant velocity. And hopefully you remember from our discussion from earlier this week or from whenever we did it, if this box is moving at a constant velocity, that would be an example of equilibrium, right? And equilibrium means that the net force has to equal zero. Here, even though it's not a free body diagram, it is a picture showing forces. There are four forces that act on this box. There's the force of this hand pulling it along that they've labeled F. If we want to be a little more specific to it, sometimes we'll see it referred to as F of A because it's an applied force. And then we got the weight of that object, the gravitational force acting down on it, m times g. All right? Now, if this object is going to be moving at a constant velocity, horizontally, same speed, same direction, there has to be two other forces on this object. First, there has to be a force in the upward direction. Blue has to be exactly the same amount as green so that we balance out forces in the vertical dimension and the box doesn't accelerate up or down. We learned earlier in this chapter that we call that the normal force. Then there has to be one last force that's acting on this object. I'm going to go brown for this force. And it has to go in that direction. That force has to be exactly equal to this applied force so that the forces in the horizontal dimension are balanced and it doesn't accelerate to the left or to the right. We refer to that force, you'll see I have a bunch of things crossed out here because my old book refers to it as something, but the IB book refers to it as dynamic friction. A lot of books you'll see refer to it as kinetic friction, but we're going to refer to it as dynamic friction. So I'll label that as dF, force of dynamic friction. And as we pull this box along the floor at a constant velocity, dynamic friction has to exactly balance out the applied force so that we have net force equal to 0 and we have equilibrium. Now, I think most of you would probably realize that if I said put another box on top of this one, or maybe these are bricks, okay? It says adding a second brick, so they are bricks. Adding a second brick will increase one force on this drawing. That's the gravitational force. Because remember, gravitational force is equal to the mass of an object times g, or 9.81. All right. That'll automatically cause an increase in the normal force. Remember, those two have to balance each other out so that we don't have acceleration up or down. And if you look at it, I didn't exactly draw them the same, but do your best. I think most of you would be able to kind of realize intuitively that if I still want to pull this double brick the same speed as I was pulling the single brick, constant across the table, I'm going to have to increase my applied force. Right? Something's heavier, you got to pull it harder in order to make it go as fast as something lighter. But if it's still moving at a constant velocity, that means my dynamic friction force also has to increase. Because, remember, constant velocity means that net force has to equal 0. Whether it's a heavy object or a light object, net force still has to equal 0. The point of this being that this force of dynamic friction that is acting on an object depends on other forces. It depends on the applied force if we want to make it move at a constant velocity. But more importantly, it depends on the normal force. There is a direct relationship between the normal force on an object and the force of dynamic friction. And as you can see here, right, it says adding a second brick doubles the normal force, which doubles the force of kinetic friction. Or in this case, we called it dynamic friction, right? So, dynamic friction is a force that acts between sliding surfaces, and it depends on the normal force. We summarize that relationship. Oh, wrong one. We summarize that relationship. Stand by, everybody. Got some slide problems. I'll be back. All right, sorry about that, everybody. Let me close this up. Okay. All right, so dynamic friction acts between sliding surfaces and depends on the normal force that is acting on that object. We summarize that relationship with this equation. F of k equals mu sub k times n. Or, if we apply it to how we're going to do it, wrong color, F dynamic friction is equal to mu sub d times F of n. This equation and this equation are the same thing, just with some different letters. This Greek letter mu we refer to as the coefficient of kinetic friction. The coefficient of kinetic friction relates surfaces. Things that are rough or things that are not smooth would have a high coefficient of friction. Sand, sandpaper, the gravel outside in your driveway, or cement on the road. These are things that have or rubber tires that grip the road. These are things that have very high coefficients of friction. Now, the coefficient relates to surfaces. It only tells you about the surfaces that are involved. The force of kinetic friction, or the force of dynamic friction, as your book refers to it, is object specific. That's how much friction is acting on a particular object that is experiencing friction. Tires on a car and tires on a semi-truck, as they drive along the same road, will have the same coefficient of friction. Why? Because the tires and the road are the same surfaces. But the semi-truck and the car will not experience the same force of friction. Why? Because the actual amount of friction, or the force of friction that would show up on a free body diagram, is proportional to the normal force. Trucks have way more normal force than cars do. And therefore, even though their tires may be the same and their coefficient is the same, because the actual car or the actual truck has a greater normal force than the car does, the force that that truck experiences will be different than the force that the car experiences. But the coefficient summarizes the surfaces that are involved, right? Bicycle, car, semi-truck. All of them would have the same coefficient of friction as they drive down the road, because their tires are all very similar and the road is similar. But each one of them would experience a different force of friction based on the different normal force that each of them has. So to summarize, properties of dynamic friction. First, it always opposes motion. If this salt shaker is moving towards the right, it will experience a force of dynamic friction to the left. Friction always opposes the motion. It is proportional to the normal force. This salt shaker is experiencing a gravitational force this way, the weight of the object, and then that means it experiences a normal force in this direction. If the salt shaker is not moving up or down, those two have to be the same. Therefore, if we fill the salt shaker up, with more salt, that would increase this, which would automatically have to increase this. In turn, this one would increase as well. Okay? It's proportional to the normal force. It's the same regardless of the speed of the surfaces. The amount of friction that is acting on this salt shaker, if we slide it slowly across the table and if we slide it farther or faster across the table, is the same force. Now, it takes longer for the salt shaker to slow down because same force causes same acceleration. The same acceleration would take longer to slow a fast object down than it would to slow a slow object down. And also, same regardless of the area of contact. If we were to flip this salt shaker, now I realize the whole thing's going to move here, okay? But if we were to flip this salt shaker this way, now I realize the ground moved, but if we could keep the ground in the same spot, if we were this talented to balance the salt shaker just on this point right here, right, as it slid across the table, it would have the same force of friction as when we slide it down onto, or put it down onto its side, okay? Because the surfaces are the same, the normal force is the same, therefore the force of friction is the same. Okay? All right, so dynamic friction deals with things that are moving. But there's lots of things in the universe that don't move. And for instance, let's say, you have a car that is stuck in the grass or whatever it might be, or went off the road or stuck in a ditch. You push it, it doesn't move. Most people would say, well, that car is too heavy for me to push it. But if we talk about a car being heavy, we are referencing its mass. But remember, mass doesn't determine if something moves. Mass determines how much it moves or how much acceleration it experiences, but not if it accelerates, right? Forces determine if something accelerates. And that leads us to the idea of static friction. So, here's an object, right? It's a heavy box. Here's a table that the heavy box is sitting on. Don't know what's in the heavy box, but we want to move it out of the way because you got homework to do, right? I know you guys are diligent about doing homework. Mom put a heavy box on the table, so you apply a force to it, F of A. You try to push it out of the way, but guess what? It doesn't go anywhere. Oh, this box is too heavy. No. If it doesn't go anywhere, it is in equilibrium. There is no net force on the box. If there is no net force on the box, if you've applied a force to the right, guess what there has to be? A force to the left. How big does it have to be? Exactly the same as the applied force to the right. Why? Because now the net force is 0. That force is a frictional force. Remember the inconsistencies at the surface of the objects. They are attracting and repelling in a way that this box doesn't want to go anywhere. We refer, like it says here, static friction is due to the microscopic irregularities of the surface. Okay? This force we refer to as static friction. In this case, static friction balances out the applied force to keep the net force equal to 0 and acceleration does not occur. This picture summarizes it. If there is no applied force on the box, there is no static friction. Static friction doesn't exist on stationary things. It exists and it acts on things that have another force applied to them but still don't move. We can't have a frictional force in this direction if it doesn't oppose anything. Because if it did, that box would start accelerating to the left. Static friction does not exist on stationary objects. It exists on objects that have a force on them, but they don't move, like this example here. So static friction can be 0, but if we apply a force to the right and this box doesn't move anywhere, there has to be an additional force to the left exactly the same size. So, let's say you push that box on your dining room table or your kitchen table because you're trying to do your homework. It doesn't go anywhere. Your natural response is going to be, all right, I'll just push harder. But guess what? That's a big box, and it still doesn't go anywhere. If it still doesn't go anywhere, even after you've pushed harder, guess what? The net force is still 0, and that means that your applied force has gotten bigger, but that means that your static friction force must have gotten bigger to keep the net force equal to 0. Static friction can adjust to the other forces that are acting on that object to keep the net force equal to 0. That is summarized by this graph right here. Notice, frictional force on the y-axis, applied force on the x-axis. This is how hard we're pushing on that box. This is the frictional force that exists. If we don't apply any force, if there's 0 force, there's 0 frictional force. That is this point right here. But if we apply a small force, the box doesn't move. That's this point on the graph, right here, where applied force and frictional force are exactly the same. We pull a little harder. frictional force, or that box still doesn't move. If the box still doesn't move, that means the net force is still 0. Applied force, frictional force, still exactly the same. But that only happens up to a certain point. Static friction does not increase indefinitely in response to any applied force. If it did, nothing would ever move because the net force would always be 0. Clearly that's not the case. So there is a point where static friction reaches a maximum level. At the maximum static friction, right? That's what we refer to this frictional value. The maximum static friction. The net force is still 0. If it's static friction, it's not moving. And if it's not moving, acceleration is 0, net force is 0. However, if we apply a small amount more than the force we applied at the maximum static friction value, now we would have more force to the right than we do to the left. And if that's the case, acceleration occurs. Acceleration occurs, the object starts moving. Now we become dynamic friction again. And if you see here, once sliding begins, the friction is kinetic or dynamic and has a magnitude less than the maximum value of static friction. It is easier to get things to keep moving once you get them moving. If you've ever tried to move a heavy couch or a dresser or something across a carpeted floor, it's harder to get it to start moving than it is to keep it moving once it's already there or once it's already moving. Why? Because the maximum static friction, the value that we need to exceed in order to begin motion, is greater than the kinetic friction value that exists while an object is moving. We refer to this region of this graph, let me get rid of this. This region of the graph is the static region. At that point, the applied force is completely balanced out by the frictional force, and the net force is 0. But once we exceed this maximum value of static friction, right? This point right here would be Fs max, the maximum static friction that can exist for that particular object. If we exceed that value with our applied force, we then move into this region of the graph, which we refer to as the dynamic region. Why? Because now it's moving. Notice the frictional force remains constant through this region. The y values never change, but those y values are less than the x values that we are applying to that object. This region of the graph, an object will accelerate. Right? This region of the graph here, this object is in equilibrium. Okay? So, that's how our different types of friction, static and kinetic. How much static friction is there? Well, again, it depends on the coefficient of static friction. And again, the coefficient of static friction will give us the maximum force of static friction. They are related through the normal force. If this box, right, or this brick, if there were two bricks again, just like in the picture we saw before, there would be a greater force of static friction we would have to overcome to start the motion. The force of static friction depends on the coefficient of static friction. And again, remember, this deals with surfaces, right? What kind of surface are we talking about? moving a couch across the carpeted floor in the living room is harder to start than it is to move it across the tile floor in the kitchen. But it also depends on the normal force, the actual normal force acting on that object. One thing we can show from this graph is that the maximum static friction is greater than the kinetic friction force for any particular object. Not for all objects, for any particular object. Therefore, it is harder to get something to start moving than it is to keep it moving. In most cases, the coefficient of static friction is greater than the coefficient of kinetic friction. And that means that static friction is usually greater than the force of kinetic friction. Again, it's harder to get something to start moving than it is to keep it moving. So, friction, two types, static and dynamic. Static keeps things from ever moving to begin with. It keeps the net force balanced out at 0. Right? It can change depending on the applied force or what else it's opposing. But once something starts moving, that changes into dynamic friction, right? Which is a constant value as long as that object keeps moving. So next couple days in class, we'll look at some more examples. We'll do some calculations. How much static, how much dynamic friction is there on an object? And we'll start looking at it numerically.